In this class, we will discuss stereochemistry of addition reactions. We will take a double bonded compound as example. The compound is stilbene. We have the formula C6H5 CH double bond CH C6H5. Now we have on each carbon one hydrogen and one phenyl ring is there. So this molecule can show cis trans isomerism. So you can write C6H5 C H double bond C H C6H5. This is trans stilbene. Trans stilbene. And here we have H C6H5 C6H5. So this is the cis form of the compound. If you treat this with bromine, molecular bromine, in suitable solvent, maybe CCl4 we can take, we will have addition product C6H5 C Br H CH Br C6H5. So this is a product of it. We can see we have two asymmetric carbons. So we expect 2 power 2 number of isomers as the product. That is 4 isomers. But since we have a planar symmetry here, this is one of them, one pair will be meso. And therefore, there will be 3 isomers only. So we won't get 4 isomers, we'll get 3 isomers. So since this molecule, the starting material is not optically active, the product will be either racemic mixture or a meso compound. So during this addition, which will give the meso compound and which will give the DL mixture? That is what we have to find out from the stereochemistry of the reaction. And then see whether it is a stereospecific reaction or stereoselective reaction. Okay, so we will make a model of this molecule first. So if we make a model, the model of the molecule looks like this. Here I have a hydrogen, a phenyl ring. On the back side, I have a phenyl ring and a hydrogen. And you can see here, this is the lobe of the pi bond. It's a p orbital, 2 p orbitals overlapping to form a pi bond. So this is the model. Now let me rotate this way. If I rotate this way, you can see all the sigma bonds are the plane of the board, and the pi bond is in a perpendicular plane. So the pi bond is perpendicular. Now let us see how we can draw this on the paper. So if we try to draw this on the paper, let us use the whiteboard and try to draw it. So first, we'll keep all the sigma bonds in the plane of the board. So I draw all the sigma bonds C6H5 H C6H5 phenyl ring and H. So we have all the sigma bonds, 5 sigma bonds, 1, 2, 3, 4, 5. Now we have the pi bond which is perpendicular plane. So I will represent the pi bond with the lobes, the two lobes overlapping with each other. So this is how it looks like. So this is the front lobe. On the back side, we have this back lobe. Like this. Now suppose I rotate this molecule in this fashion. If I rotate in this way, I can represent, I will like to represent this in a horizontal fashion. This has become, all the sigma bonds have come from zone in a perpendicular plane. You can see that. Now it is horizontal. So I have to draw, and these two bonds are coming towards the observer, towards us, and these two are away from us. So let us draw that. So one pair. Sigma bond. So I will draw the C6H5 here. This is projecting towards you, and while the C6H5 on the other side is projecting away. So you have the H and H. Now this is the p orbital or pi bond. So this is the pi bond. Now, if we look at the molecule, if we observe this molecule, we can do an attack on the bromine using a bromine atom. This is a bromine molecule. Now remember, bromine has got a lone pair of electrons here. So this is Br. You have lone pairs, 3 lone pairs on each of these Br. That you should not forget. Now let the bromine approach the molecule. Bromine approaches, it has all the possibilities. It can approach from here, it can approach from here, from here, from here. But none of these approaches will make the bonding with the pi bond. So if the pi bond has to react, the bromine has to approach from the upper side. Okay, the bonding orbital, it approaches from the upper side and forms a bond with the pi bond. Now what happens is, if you write how a curved arrow mechanism for this, we will be able to write like this. You can see here, the bromine is approaching from the top. Remember, it can approach either from the top or from the bottom. So let me draw this bond from here. Here is the bromine. Yes. So we have the lone pair of electrons. Okay. So now, if I make a small modification, I remove this and show it as a pi bond. Let me remove this and show it as a pi bond. I'm drawing it as a pi bond. Now, what happens is this lone pair attacks on this carbon, and this pi bond attacks on the bromine. Okay, then the pi bond attacks on this bromine. This will act as a leaving group. So all these three occur simultaneously. So for understanding purpose, we will consider it like this. We will remove this. To understand this clearly, first we'll remove this one. Now see here. Suppose we do this attack. Suppose we are doing this attack. But naturally, this is a sort of substitution reaction. The bromine should leave, and it will form a bond here. It will tend to form a bond here. right? That is, the bond will be formed. Yes. The new bond is going to be formed here. And this bond will break. This bond breaks off. So this is a sort of substitution step. Simultaneously, this also attacks here at the same time. That means this it forms a dative bond here. So we can show like this. So we can write this as C6H5. You can see C6H5 is on the back side. H is to the front. And now remember this bromine is in the plane of the board. And now see this is from a dative bond. Therefore, this Br will attain a positive charge. Now, what was the leaving group? The leaving group was Br minus. Br minus. Now, so we have the hydrogen here. So this is what is happening. So if we look at the model, it is attacking from here, and it forms a bond with the bromine atom. And this bromine leaves off. This goes out as Br minus. So if we make a clear-cut model with the bonding, let me remove these lobes and make 2 pi bonds. You can see here. One is here. And the second one is here. So it's a bit difficult. I will just take another type of bond here. This will work well. I have a second one. See here. This is how it looks like. This is how it looks like. So this is the bromine atom. Now remember, this bond is formed by the lone pair of electron. This is a rearranged or reoriented pi bond of the double bond. Double bond, pi bond of the double bond C between C and C. And now your Br minus has escaped. The Br minus has come out. And remember, now let us, so this is the molecule like this. You can see this is in a perpendicular plane to the plane of the sigma bonds. So once we have found this, and this is called a cyclobromonium ion. So this is the cyclobromonium ion. Since the Br is on the upper side, you can see, you can expect this C6H5 and this H to bend a little down, just like this also. Slightly down. Okay. Now what happens? In the next step, what happens is the Br minus attacks in an SN2 fashion. Now this Br minus can attack in an SN2 fashion. Now here is my Br minus. This is the Br. The Br minus can attack either from this side, from here, or from here. So if it is attacking on this carbon, you can see it is approaching from the opposite side because it is a least hindered side. It comes and forms a bond here. So now you have to substitute, so a substitution occurs, and this goes off. Yes. Yes. So the bromine opens from this side. So this bond is broken and Br comes here. Now you can see here, you can look at the stereochemistry of this. Let us draw this structure. What product is formed? Let's draw this structure. So Br minus comes from below. This gets broken off. And what do you get? We get C. So when this bromine comes here, here is this bromine, and we have the bromine coming from the opposite side, and here I have the hydrogen. This is C6H5. And over here, the C6H5 is to the front, and here is the hydrogen. Okay. Now let us see what is the geometry of this. Whether this is. Now what we'll do is we'll rotate this. Only this carbon clockwise. We are going to rotate this carbon clockwise and bring them on the same side as the substituents. So if you look at this, you can see this bromine and bromine are matching. This hydrogen is matching. Phenyl ring is matching. So this is the meso product. So this is the meso product. Let's see how we can draw it. Suppose you rotate this. This bromine will come here. Br. And this C6H5 will come to the front. C6H5 will come to the front on both the sides. C6H5. And over here, the hydrogen will go to the back side. Hydrogen on the back side. So if you draw a Newman projection, this is a meso compound. You can see here, this is a plane of symmetry. If you draw a Newman projection, it will be this one. C6H5 and C6H5 and H and H. So this is a meso compound. Okay, so if you start with the trans stilbene, you will get the meso product. Suppose you start with the cis stilbene, you will get the opposite direction. What we have to do is only one thing, that is exchange this. No other change. Change it. So if you change this, you'll get this as, this can be replaced by H, and this can be replaced by C6H. That means you'll get a DL mixture. So trans stilbene gives meso product, while cis will give a DL mixture. And remember, you won't get a DL mixture from trans, nor you will get a meso compound from this cis. And therefore, this reaction is stereospecific. This reaction is stereospecific. So this is the geometry of addition reaction of bromine molecule.